Okay, we're going to try a little bit different format for our lesson. I want to be able to write on the paper, so we'll try it this way and see how it goes. So what we're going to be looking at now, so taking this the next step, we've learned how to draw shapes. We've learned how to predict, draw Lewis structures. We've learned how to predict shapes. We've learned how to figure out angles, bond orders, all this information, and now we're going to start to apply some of it in some other facets of what happens with molecules. But there's one more thing that we need to understand, and that actually two more things, and that is bond polarity and then also electronegativity, because that's going to play a part in what we're going to be doing with this. So again, we've been dealing with covalent bonding, and we said that covalent bonding is when you have two atoms and they're sharing electrons, and they share electrons in order to get their full octets. I haven't shown all the electrons on this molecule technically, of course there's more electrons around, but each atom has its 8 electrons. The point is these two right here are being shared. Now, all we've said is that they're being shared, but in actuality, some things are going to share better than others. And what I mean by better is more equally than others. So in this first example that we have here, you see that the fluorines, you have two different fluorines and you have a single bond, 2 electrons in between them. You can see that these electrons are being shared equally. And the reason why I say you can see it is I've literally drawn the 2 dots directly in between the fluorine and the fluorine. If you notice in this example, they're being shared. Hydrogen still has the 2 and the fluorine, of course there's 6 more on there too. The fluorine has its 8, but you notice how I've drawn these electrons being unequally shared. Okay, you can see that it's being unequally shared, and all of that, how you decide whether or not there's equal sharing or unequal sharing, is going to come down to this electronegativity concept. So if you take a look down at the bottom of your paper, this is a table of electronegativities. You don't have to memorize it, you just need to be able to use it. And what you're going to do is look at the atoms that are sharing the electrons, and you're going to look at their values of electronegativity. Now you can see that the definition of electronegativity is the ability of an atom in a molecule to attract electrons to itself. Okay, so it's kind of like electron affinity, but we're not really going so far as to say gain an electron. That's more an ionic bonding thing. This is more about sharing, how well it can share electrons and whether or not it's going to hog electrons. If you find fluorine on the list, fluorine actually has the highest electronegativity out of all of them. And then you can see all the values kind of decrease. There are trends for electronegativity. Again, we're going to kind of use it in context for what it's supposed to be. You notice the noble gases don't have any values for electronegativity because they don't really want to share, and we know that about them as well. So if you come back up here and you say, okay, well, fluorine has an electronegativity value of 4.0, and then of course this fluorine is fluorine as well, so they both have an electronegativity value of 4.0. If you think about that 4.0 value, it's essentially how hard the atom is pulling, how much it wants those electrons. Well, if both of them are pulling with 4.0 value of electronegativity, then they're sharing. I mean, they're both pulling the same amount. So what we do is we take these electronegativity values and we find the difference between them. And you can see that you have a difference of 0. And a difference of 0 means you must have equal sharing going on. That type of covalent bond is called a non-polar covalent bond. Thus far, all we've called them is covalent bonds. But that is a non-polar covalent bond if you have equal sharing, if the electronegativity difference is like this problem. And we'll do a little bit more with that in a second. Let's look at what polar means then. Polar means you have an unequal sharing. Okay, they're not being shared equally. And so if you look at the values down at the bottom of your table, for hydrogen you have 2.1, and for fluorine you have 4.0. So hydrogen is not being sharing the electrons the same way fluorine is. Fluorine is a big hog, and it's hogging the electrons over closer to it. It doesn't mean that hydrogen doesn't still have them. He thinks he does, and that's fine, but fluorine is definitely holding on to them. So that's what makes that a polar bond. So now we should be able to look at bonds in between atoms, and we should be able to tell whether or not they're polar or non-polar. I'm sorry, I pointed at the wrong one. Non-polar or polar, and that is using this electronegativity table. Okay. Now, if you flip your paper over, this is how we're going to represent these bonds. So when we have a non-polar bond, sorry, back on this side, we have a non-polar bond, we just don't do anything. So if I was to draw this out, I could use my line, of course. we know it's equal sharing because this one's 4.0, this one's 4.0. We just don't do anything. But when it looks like this, we need to have a way to distinguish that we've acknowledged that it's a polar bond. And the way we do that is one of these two ways. If you want to put a star next to this way, please, because that is the one that we will use much more commonly. And so the first way, or the way that we'll use more commonly, is you take this weird looking arrow and you draw it over the bond. So let's say this was drawn a little bit more traditional. This is what we would have drawn in our homework. To draw the arrow, you're going to put the tip of the arrow, which is here, over the more electronegative element. So we said that this one was 2.1, this one was 4.0. So whichever one has a higher electronegativity gets the tip of the arrow. That's one way to do it. The other way is to use these partials. It kind of looks like a figure 8 that hasn't been completed, okay? Use a partial positive and partial negative because you're saying that the electrons are hogged over here on this side by fluorine, which means there's a little bit more negative charge going on over here than here. Not enough to call it a full positive and negative, but partial. And again, that's what that little symbol that looks like that is it is a partial. Now, how do you determine whether or not it's equal or equal enough? Comes back to those electronegativity differences. If you remember here, we said the difference between these two were 0. And if it is 0, you know for sure that that qualifies as equal sharing. But if your difference was anywhere from 0.4 to 0, so anything 0.4 or less, that's going to be a non-polar covalent bond. So that is going to be what we consider equal sharing. Okay. If your difference is greater than 4 but less than 2, then that we're going to call unequal sharing, which in other words is called a polar bond. And if we go back to this example, if we found the difference between these two, you'll see that the difference is 1.9. So 1.9, if we come on here, falls within this range. So that's why we said that that would be a polar covalent bond. And then anything with a difference of 2.0 or higher or approximately, that's actually ionic. That means it's not even sharing anymore. That means it completely transferred because one was hogging so much that it actually caused it to completely transfer over to the other atom. Now, these do have a little bit of gray area. Most textbooks accept that these are the values that we would use. Okay, so let me show you what this would look like. And we're going to eventually do this with molecules, but there's a lot more to it when you have a molecule involved. For now, you're just going to be looking at literally two atoms that have a bond in between and trying to decide if the molecule is polar or nonpolar, and then it actually wants us to figure out which ones are more polar. So what you're going to do is you're going to use your electronegativity table and start by looking at what their electronegativities are. So if you look at your table on the other side, you'll find that boron is 2.0, and you'll find that iodine is, sorry, I don't have my table ready, 2.5. Okay, so you find the difference between those. The difference between those is 0.5. According to our chart, between 0.4 or less is nonpolar, but between 0.4 and 2, that would be polar. So this right here is a polar bond. If it's polar, then we need to draw our little arrow. That's how we tell people that it's polar. So the tip of the arrow goes over the more electronegative one, which is this 2.5. So we're going to draw our arrow like such. Okay, so that's our first one. The second one we're supposed to compare it to, of course, boron is still 2.0. If you look up chlorine, chlorine has a higher electronegativity than iodine did. So the difference between the boron and the chlorine is 1.0. Now that still makes it polar, which means we still need to draw an arrow. Tip of the arrow always goes over the more electronegative one. Now you see these two are polar. They want us to figure out which one's more polar. So the answer is going to be this one because it has a larger difference in electronegativity, showing that one is hogging more than the other one is. Okay, so let's go ahead and try this one. And if you want to pause it and try it, and then you can come back and check it. So the electronegativity of Si is 1.8. The electronegativity of oxygen is 3.5. The difference between those two is 1.7. Now this one hopefully right away sticks out to you. Maybe you had to put in the numbers, but if it's two of the same element, it has to be nonpolar. There really isn't a choice because you know it's going to come out to be 0. So this one here is polar, and this one here is nonpolar. Now if it's polar, you have to draw the arrow. It's a designation you have to put on it. So tip goes to the more electronegative one, and then to answer the more polar question, this one would be the more polar one because, well, frankly, it's polar, right? The other one's nonpolar, so obviously the polar one is more polar. right, you can pause again on this one if you want to try it, just as a hint. The double bond makes no difference whatsoever to the electronegativity, because electronegativity is a measure of the nucleus pulling in those electrons. So carbon, you should have 2.5. Oxygen, you should have 3.5, if you look up those values. Difference, 1.0. Makes this one polar. I'm going to put the tip of my arrow over the oxygen. Sorry, I didn't leave myself enough space there. And then carbon here is 2.5. Sulfur is 2.5 as well. Now they're different elements, but notice they had the same electronegativity. So when you find the difference, it's going to be 0, which makes this one nonpolar. Okay, so the answer is that this one is the more polar one out of those two. So the double bond makes no difference to what you're doing with this. So you're just going to find that difference in electronegativity. And like I said before, I'm not going to make you memorize the electronegativity, but you do need to know this. Okay, and you obviously need to understand the idea of polar and nonpolar and know where those designations fall.
First things first, I'm the realest. Drop this and let the whole world feel it. And I'm still in the murder business. I can hold you down like I'm giving lessons in physics. Right.